Right, so first let's recall what a t-test is actually doing. A t-test compares two groups or two means. On the other hand, ANOVA compares three or more means all at the same time. And by doing so, it's accounting for that type 1 error so that we can be more confident in any significant difference that we see. And now, what this means is that a significant ANOVA tells us if there's a difference somewhere between our groups, but it's not going to tell us where that difference is. So in the coming weeks, you're going to learn about post hoc comparisons and pairwise comparison. But it's important to keep in mind that when interpreting the ANOVA output, we can't actually come to the conclusion of which groups are significantly different from each other. We're just going to say whether there's a significant difference somewhere in our data. All right, and now this week we're specifically running a one-way ANOVA. This simply means that we have one independent variable of interest, and specifically an independent variable with three or more levels. And levels are essentially categories. So in this case, our independent variable is exactly the same as it was in the t-test. We're still interested in whether soy meals influences sperm count. This time we have four levels of soy meals. So the four levels here are, again, no soy, 1 soy, 4 soy, and 7 soy. Okay, so we have one independent variable with four different levels. This is different from a numeric variable here. Here, our independent variable is categorical. Even though we're working with 0, 1, 4, and 7, these are categories of number of soy meals eaten, not necessarily a ratio scale. So the independent variable, number of soy meals, is categorical. And our dependent variable of sperm count is numeric. Okay? Now this is really important because one of the assumptions of ANOVA is that our independent variable is categorical. So in this unit, if you have an independent variable that's numeric, you know that regression is going to be best suited. However, if the independent variable is categorical, ANOVA or t-test is probably going to be what you want to consider. And from there, the number of independent variables you have will define whether it's a one-way or a factorial ANOVA. And the number of levels in each of our variables will decide whether it's a t-test or ANOVA. Okay? This is why it's really important that before you even go in and run your analyses, you have a good understanding of what the variables are. All right, but here we're working with the exact same data set that we did last time. It's just going to be in a different format. So let's go ahead and import that new data set. The previous data set is what's called wide format, where we have four separate variables for each level of our independent variable. In this case, it's in long format, and it does have to be in long format to run the one-way ANOVA. Right, so the data set here is just called soy.dta, and we have two variables now. Now we have a variable S meal, or number of soy meals, and sperm count. We can also take a quick look at our data editor window. So we can see that we have categories now for soy meals. No soy meals and the sperm count, 1 soy meal and associated sperm count, 4 soy, and 7 soy. Okay, so now we have four distinct groups, but under one independent variable. And in long format, it's actually really nice because we can break up our output by these different groups. So we're going to actually take a look at our summary statistics using a different command rather than just summarize. This time we're going to be using the command tabstat, and we want the information for sperm count. So we want to know the information of our DV at all levels of our independent variable. So to do this, we use the command tabstat, our dependent variable, by our independent variable. So this is going to break up the output by each level of our independent variable. And we're telling Stata to print the number of observations, n, mean, standard deviation, skew, and kurtosis. So we can start to understand the shape of the distribution as well from these summary statistics. Okay, when we run that command, we get this nice, neat table here with all the information we really need at this point. Right, so the mean for each row should be the same exact mean that we saw in the t-test output, and same with the standard deviation. Now we also get again the skewness and the kurtosis statistics. I'm not going to belabor this because this is since we've covered this a couple times already, and it should be revision. But just remember that the skewness statistic greater than 0 is a positive skew, less than 0 is a negative skew. And in this case, since it's greater than 1 for 3 of these levels of our independent variable, that's highly problematic. So we've already started to violate the assumption of a normal distribution here. Because again, no soy, 1 soy, and 4 soy are highly positively skewed, according to the statistic here. And it also looks like we have some problematic kurtosis statistics as well. Remember that a kurtosis of 3 is mesokurtic, or in other words, a normal distribution. Less than 3 would be considered platykurtic, but more like less than 2 is what's considered problematic. On the other hand, greater than 3 is leptokurtic, and greater than 4 is problematic leptokurtic. So it looks like in this case, when we have a problematic skew, we are also seeing a problematic kurtosis statistic. And in fact, these 3 levels, again, no soy, 1, and 4 soy, are highly leptokurtic here. 7 soy, on the other hand, isn't perfect. It's positively skewed, but it's within our cutoffs. And for kurtosis, it's platykurtic, but again, it's within our acceptable range of 2 to 4. So it looks like 3 out of the 4 levels are already violating the assumptions of a normal distribution. And we can just take a look at that with the histogram as well. Right, this time, since we're in that long format, we can actually print the frequency distribution for all levels of our independent variable. So this command, histogram, our DV sperm count by soy meals, this will print 4 frequency distributions at the same time, which is really nice. We don't have to do all 4 of them separately like we do in wide format. All right, so it looks like we've really confirmed the problematic distributions here. These 3 distributions, no soy, 1 soy, and 4 soy, are definitely positively skewed, absolutely positively skewed here. Now, 7 soy meals, even though it was within the appropriate range, it does still look a little problematic. We might actually want to identify, if we wanted to look in more detail, we could identify, tell Stata to give us more bins. We're not going to do that today. It's not really that necessary. But what we can confirm is that we have a much smaller range or much lower variability here compared to the other variables or the other levels of our independent variable. And if you remember from the results of the t-test, the standard deviation for 7 soy meals was much smaller compared to the standard deviation for no soy meals. All right, so that's also confirmed here. So before we actually run the ANOVA, I'm going to go ahead and go through all of the assumptions of ANOVA before we move forward. Right, so there are 5 assumptions with ANOVA, and they're actually the exact same assumptions as a t-test. Right, so the first assumption we've already talked about, simply we have a numeric dependent variable, and the second assumption is a categorical independent variable. right? So we've met those two. Our DV is numeric, sperm count, and our IV is categorical, number of soy meals per week. The third assumption is simply that we have independence of observations. This simply means that no one participant was in multiple groups. And this is simply met by design. It would be really hard for someone to have 0 soy meals per week for an entire year and 4 soy meals per week for an entire year. Now, the fourth and fifth assumptions are about normality and homogeneity of variance, but specifically normality in our dependent variable at all levels of our independent variable. So the dependent variable alone doesn't necessarily have to be normally distributed, but at all 4 levels of our independent variable, the DV should be normal. And in this case, we know that that's not true. So we know that we violated the assumption of normality here. And same thing with assumption 5, homogeneity of variance. We want to confirm if there's equal variability in our dependent variable across the 4 levels of our independent variable. That simply means that our standard deviation in sperm count for no soy should equal that standard deviation in sperm count for 1 soy, for 4 soy, and for 7 soy. Now, we've already visually looked at this. We know that the standard deviation for in sperm count for 7 soy looks to be different compared to the others. Now, there are 2 ways to confirm that. There's either Bartlett's test or Levine's, and I'll show you how we can do both of those today. So I'll hold off on deciding whether we violated that assumption or not until we actually test it. But let's go ahead and fit the ANOVA model. There are 2 ways that you can do this in Stata. You'll start to notice that with Stata, there are usually a couple different ways to get to the same conclusion. Um, it'll start to become personal preference for you. So the first way to run an ANOVA, pretty simple. The command is ANOVA. Just like with regression, you want to follow that with your dependent variable. Okay, so our command is ANOVA, the dependent variable sperm count, and our one independent variable soy meal. Again, this will tell us if there's a significant difference anywhere in our data set. Right, we run the command and we get this output. You'll notice that we do get an R² value here. You interpret that the same way we do with regression. So this is saying that about 9.4% of the variability in sperm count can be accounted for by number of soy meals. So this R² is simply telling us that about 9.42% of the variability in sperm count can be accounted for by the 4 levels of our independent variable, number of soy meals. Okay? And for now, that R² is the only value that you have to interpret um, in this top table here. Right? And now finally, this table, the ANOVA table, should look familiar to you. It's that table in the regression output that I've been pretty much disregarding up until now. So in the ANOVA table, we have a line for the overall model. Okay, a line for the overall model, a line for our independent variable here, soy meal, and then a line for error. So error in our model, or variability in sperm count that we can't account for by our manipulation. And our manipulation is simply number of soy meals eaten. So one thing to keep in mind, when you have a one-way ANOVA or one independent variable, this model line will always be the same as the variable line, okay? No difference here. However, once we start getting into factorial ANOVA, where we'll have multiple independent variables, the model line is going to look different. And this model line is pretty much telling you the same thing. as the model statistics from regression. Okay, so we have an F statistic and a p-value. This is simply telling us, is this a significant model? Okay, we can usually disregard it. And that's because with ANOVA, we're really particularly interested in our independent variables themselves, because that'll tell us more information about where significant differences are. We don't necessarily need to know the overall significance of the full model. So you should get in the habit of interpreting the actual independent variable lines. And the columns that we have here are partial sum of squares. So SS stands for sum of squares. Okay. The next column is degrees of freedom. DF stands for degrees of freedom. And finally, MS stands for mean square. So both the columns for sum of squares and mean square are just telling us about overall variability. So it's essentially an unstandardized version of variability. Okay, and specifically for the independent variable line S meal, it's variability in our DV that we can account for by number of soy meals eaten. That means for this residual line, for the residual line, the sum of squares and the mean square columns tell us about variability we can't account for, or variability in the DV that isn't explained by the independent variable. That's really all you need to know for now about sum of squares and mean square. But let's talk a little bit more in detail about degrees of freedom here. With ANOVA, you do want to report a few different degrees of freedom when interpreting your output. So we can see up at the top that we have 80 observations. That simply means we had 80 participants in the overall sample. Now, degrees of freedom total is pretty simple to calculate. Degrees of freedom total is simply number of observations minus 1. So I'm going to write this up at the very top. So df total equals big N minus 1. Right. Now let's talk about the degrees of freedom for our independent variable number of soy meals. This is simply the number of levels in that independent variable minus 1. And number of levels is often referred to as K. So K minus 1 is our degrees of freedom for soy meals. In this case, we know that we have 4 levels for that independent variable. So 4 minus 1 is 3, which is how we got to our degrees of freedom here. And finally, degrees of freedom residual is also important. And that's total N minus K. Right, so total N minus the number of levels in our independent variable. In this case, it's 80 minus 4, so 76. Now, there's another way that you can come to that. Degrees of freedom resid can also be little n meaning the number of observations within each group. So little n for 0 soy minus 1 plus little n for 1 soy minus 1 plus little n for 4 soy minus 1 plus little n for 7 soy minus 1. You'll get to the same answer, or to the same degrees of freedom there. Now let's consider what degrees of freedom actually means. When we say degrees of freedom, we're really referring to the number of values in the data set that are free to vary. And let's talk about this in a little bit more specifically. So let's say we have 3 numbers here. Let's say this is a 2, this one's a 2, and we don't know this third one. But we do know that the mean for this range is 2. This is a very lame example. When we say degrees of freedom, we mean that there are 2 numbers in this example distribution that can be whatever they want to be. But based on the behavior of these two numbers, this final value here is fixed. Okay, so because we know here that these two values are 2 and we have a mean of 2, this value, this x, has to be 2. So again, just to reiterate, degrees of freedom is simply the number of values in our range that are free to be whatever they want to be, but that last value is fixed based on the behavior of the rest of our of the rest of our values. Right? So that's simply what degrees of freedom is telling us. It's the number of values that are free to vary. So I'm going to go ahead and clear out this screen so that we can talk about our F statistic and the p-value. Just like with the t-test, we have an F statistic. That's our test statistic. And we have what Stata gives us is what's called the obtained F. So this is the F statistic based on our data. And what it's doing behind the scenes is it's comparing this F statistic against a critical F. So that should sound a little familiar to you. Hopefully you've compared a T to a critical T to confirm significance levels. In this case, Stata is comparing the F statistic against a critical F based on these degrees of freedom. And then it's adjusting our p-value from there, okay? So the good thing is Stata is doing all of this for you. You don't have to worry about what the actual critical F is here. You just have to look at the associated p-value to confirm if this ANOVA is significant. Is this ANOVA model significant? And just like with pretty much every other p-value we compare, p of 0.05 is going to be our level of significance here. All right, so let's write out the null and alternative hypotheses before we interpret. All right, so the null hypothesis for this one-way ANOVA with one independent variable and 4 levels simply states that mean for 0 soy equals mean for 1 equals mean for 4 equals mean for 7. Basically, there is no mean difference between any of these groups. The alternative hypothesis, on the other hand, simply states that there is a significant difference between 2 of our means, at least 2 of our means. Okay? Now again, let's think about what that alternative hypothesis actually means. This says that we have 4 groups, and to reject the null hypothesis, there should be a significant difference between 2 of these means. All right, we're not saying where that significant difference is. It could be between 0 and 4, between 1 and 7, between 4 and 7, and so forth. We just want to know if there's a significant difference somewhere. Now, for these example data, we have an F of 2.64, degrees of freedom 3 and 76, and our p-value is 0.0558. So we have not technically met the cutoff of significance here. This p-value is telling us that there is no significant difference between any of these groups. All right, now what you could say is that these are marginally significant. You might see that quite a bit in journal articles. It really depends on the journal and the lab group, but you might say that these are marginally significant. This is a marginally significant ANOVA, so you will go ahead and run what we call post hoc analyses to confirm where a significant difference is or where the difference is. So that will be defined by, the journal or the field, whether this would be considered marginally significant. But in this case today, since we have violated some assumptions of ANOVA, we would probably take this p-value here with a grain of salt, okay? Now, the last thing I want to do before I demonstrate another way to perform a one-way ANOVA is just let you know how we get to this F statistic here. So you can actually come to this answer from the information in this table. So let's say, for example, on a quiz or an exam, you're only given this information and you're not given the F statistic. You can actually come to this answer pretty easily. just through some basic division. So the first thing that you want to do is divide your partial sum of squares here, divided by 3, your degrees of freedom, to get your mean square. Okay? Remember that the mean square is variability explained by our manipulation. Right? And you also want to get the mean square for the residuals. And that's simply sum of square residual divided by degrees of freedom residual. Right? And that brings us to the mean square. Now, finally, to calculate the F statistic, you simply divide mean square divided by mean square error. This essentially makes the F statistic a ratio between variability accounted for by our manipulation divided by variability unaccounted for. So, change the color. F equals variability explained by the manipulation divided by variability not explained, or rather error. Right? Again, this simply means that our F statistic is a ratio, and a ratio between variability we can explain divided by variability we can't explain. Right? And because of that, the larger the F is, the more variability we're actually explaining by our manipulation. All right, so let's move on to finally test the assumption of homogeneity of variance, specifically using Levine's test. Now, this is one example where the stata command isn't quite intuitive. Levine's test is the command robvar, that stands for robust variance, right? And we want to determine if we have equal variability in sperm count at all levels of soy meal. Okay. Now we run the command. Again, we get the average value or the mean, as well as the standard deviation here. And Levine's test, similar to a Shapiro-Wilk, tests against the null hypothesis that there is equal variability at all levels of the IV. Okay? This means we would like to fail to reject this null hypothesis, or rather that the p is greater than 0.05. Now we have a couple different p-values in this output. Really all you need to know is that you should interpret this top one. Oops. This top line here. This is testing variability around the mean, or standard deviation. The other lines you'll never have to interpret, but just so you know for your own reference, W50, that's testing variability around the median value, right? And then W10 essentially removes data at the tails, so 5% of the data at each tail, and assesses Levine's test from there, right? But you only need to interpret this top line. Right? And in this case, as we can see, the p is less than 0.05, which means we reject the null hypothesis that there is equal variability between groups. And as we already expected, we have violated the assumption of homogeneity of variance. Okay, so if we pop over here again, we've met 3 of the 5 assumptions. If you're doing your own work, you would probably want to do what's called a non-parametric test. This is something that you're going to learn, I believe, in weeks 12 and 13. But for now, we'll just go ahead and interpret the results and move on from there. Non-parametric tests basically have no assumptions about the distribution. But again, for now, we're just going to go ahead and interpret our ANOVA output. And let's do that by running one more command. This is simply another way to get the same exact results we saw with the other ANOVA output. All right, and the command here is simply one way. That's telling Stata we're going to do a one-way ANOVA. Again, our DV sperm count and our independent variable soy meal. Okay. Now, the output looks a little different, but you'll notice that our ANOVA table doesn't tell us anything new. Okay, this has the exact same sum of squares, degrees of freedom, mean square, and F statistic. Now, the good thing about this command is that it does give us our summary statistics. So we have our mean and standard deviation, which is always helpful, but it also prints Bartlett's test for equal variance. Bartlett's is very similar to Levine's, and you interpret it the exact same way. All right, so we have a p-value here. Again, it's less than 0.05. This tells us that we reject our null hypothesis, that we have equal variability across all levels of our IV. So let's go ahead and move on to step 8, which is the final conclusions. This is where we interpret the output or interpret the results. And you can write this out in two ways. First, what these results are telling us is simply that this one-way analysis of variance tells us that there is a 5.58% chance of obtaining an F statistic of 2.64 on 3 and 76 degrees of freedom if the null hypothesis were true. So if the null hypothesis were true in the population, that there is no significant difference in sperm count, we have a 5.58% chance of obtaining this F statistic. This kind of demonstrates how arbitrary a p-value of 0.05 is. So if a p is 0.05, that means we have a 5% chance of obtaining this F statistic. But because we want to keep some fairly strict cutoffs, we would still say that this is non-significant. Remember, this number here, this percentage, this simply comes from the p-value. All right, and finally, to write this out in APA formatting, you would say that there is no significant difference in sperm count based on how many soy meals men ate per week. And we have our F statistic with these degrees of freedom. Remember, this is the IV degree of freedom and degrees of freedom error, our F statistic, and our p-value. Now, one thing that you would want to mention in this interpretation is that we have violated some assumptions of ANOVA. That would be important for the reader to know, okay? So that brings us to the end of this practical. Make sure that you can run through all of these commands on your own and interpret the output. If you have any further questions, make sure to reach out to your tutor. All right, and have a great week.